I'm back with another video, and in this video what I'll be demonstrating is the solutions to the Factorial Anova homework problems that I posted a few days ago. I'll also have a couple of extra problems like the one that you see here that I'll give walkthroughs on. And the reason why I have it set up like this is so that I can type in the cells as needed. When I get to a few of the later PowerPoint slides, I'm going to go full screen and use some animations. But in this one, I want to type in the answers. So when we have a table like this, when we see something, a Factorial Anova summary table, where some of the information is missing, the idea is that if we know how these different components work together, then we'll be able to figure out all the different missing parts. And it's my belief in teaching stats over the years that doing problems like this really helps students understand how these tables work together. So when you see a table like this in a publication, you'll have a better understanding of what the numbers are actually telling you, and you'll be able to figure out more pieces of information from a publication than you would otherwise be able to. So where do we start? You know, there are several different places where we can start, but one thing to know is that the degrees of freedom total is based on n minus 1. So if this number is 47, that means there have to be 48 participants in this particular experiment. Now we don't know what the other parts are yet, but we'll be able to figure that out. One thing that we can put in fairly quickly, it doesn't lead to anything else, but we can do this part of the problem. Any of these numbers here, any of the mean squares, whatever those numbers happen to be, they all get divided by 2.5. They all get divided by the within group's mean square in order to get f. So we can solve this one right now. This has to be 2.00. It's 5 divided by 2.5 gives us this. So if nothing else, that's a good place to start. And we can go this way along this row for the interaction effect, because we know that in each one of these cases, the sum of squares gets divided by its respective degree of freedom in order to get the mean square. The sum of squares is the sum of the square deviations from the mean. Depending on which type of mean that you're using, whether it's the grand mean or the column mean or the row mean, etc. The number that we have here represents a squared deviation of how much you have for the columns, rows, and interactions, or the cell means, as they deviate from the grand mean. So what we're going to do is we're going to take the interaction sum of squares of 25, divide that by 2, and that number goes here, and that is 12.5. So far so good. And then we can also get the f-test result for the interaction effect, where that's 12.5 divided by 2.5, and that gives us 5. So now we've got a few different pieces of information in, but we're sort of stuck. And the key to this one, the key to figuring out everything here, is that and you might have found this one to be a little tricky, because there's only one way to get past this stage. This degrees of freedom for the columns is c minus 1. It's the number of columns minus 1, but we don't know what that is. The rows operates on the same principle. It's the number of rows minus 1. So if we see that the number here is 2, that tells us immediately that there are 3 rows in the experiment that we're looking at. In other words, whatever the design of the experiment, the row independent variable has 3 levels to it. And then the interaction is defined by c minus 1 times r minus 1. In other words, whatever number you have here times whatever number you have here yields this one. So there's only one number that this can be, and I hope you know what that is before I type it in. It's the number that when you multiply it by the row degrees of freedom, the product of those two numbers gives you the interaction. So that has to be 1. 1 times 2 gives you 2. There's only one thing that this could be. If you know these two, you can figure out this one. If you know any two of these, you can figure out the third one. Now, all of these, all of the columns, rows, and interaction degrees of freedom all come out of the between groups degrees of freedom. And it's the same thing over here for the sum of squares. The columns, rows, and interaction sum of squares are all partitioned out from the between group sum of squares. So if you have any two of these, you can figure out the third. Well, we only have one of these, so we don't know what the other two are. But we can figure that out now because we have these. So if we know what these are, and if we know that all three of these pieces of information, the columns degrees of freedom, rows degrees of freedom, and interaction degrees of freedom all come out of the between groups degrees of freedom, then another way of saying that is that if you add them up, they'll equal the between groups degrees of freedom. So that has to be 5. 2 plus 2 plus 1. Now, just as you can move in this direction, 25 divided by 2 gives you 12.5. You can also go in the reverse direction where this number times this one. 5 times 1 gives you this. So that has to be 5. Okay, now we're moving fairly quickly, and you can see that the rest of this is going to fall into place rather easily. The rows has to be the number that is left over after you subtract 5 and 25 from 60. So 5 and 25 together is 30. Take 30 out of 60, and what you're left with is this. And my numbers aren't lining up because I got some extra spaces in there, which is kind of making it look a little lopsided, but that's okay. So again, 60 gets divided up into these three components. 5 gets divided up into these three components. So now we can go in this direction. Excuse me. 60 divided by 5 gives us this. That's 12, mean square for the between groups. And then 12 divided by 2.5, this number divided by 2.5 gives you the f-test for the one-way ANOVA, and that comes out to be 4.8. 30 divided by 2, moving in this direction, 30 divided by 2 gives you 15. And then 15 divided by 2.5. 15 right here divided by 2.5 gives you this answer, which is 6. And you can see that I'm taking them all out to the second decimal point. You don't really have to, but it's nice to be consistent with AP. Got those extra spaces in there, which is annoying to me. Okay, so now we've got these 3 cells left that we need to figure out, and the way to do that is to recognize that this number, the between groups, plus whatever this happens to be, gives you the total degrees of freedom. So again, this number from the one-way ANOVA component here, this number plus the within groups, which is the error term, the within groups adds up to the total. Sum of squares between plus sum of squares within equals sum of squares total, and by the same token, degrees of freedom between plus degrees of freedom within gives you degrees of freedom total. So 47 minus 5 leaves us with 42, and then we can go in this direction, reversing the direction here. 2.5 times 42 gives us the answer over here, 105. And now we can take the between groups plus the within and get the total, which is 165. And there's your answer. There's your set of answers for this problem. Okay, now let's go on to the next one. Now this is a new one that I did not give you. Maybe pause the video for a second and see if you can figure this one out on a scrap of paper. I'm going to fill in the blanks here. And think if I were doing this in class, what I would be doing is I'd be asking you, tell me which piece of information I can fill in next. And so as if we were in class, we can address this problem. It's rather easy to see this one. 60 divided by 1 gives us 60. And I've got a different font over there. Very odd. 40 divided by 2 gives me 20. And, well, I don't know what to do next. What do you suggest? Going on the principle that this number, well, let's see. So columns, degrees of freedom is C minus 1. The row degrees of freedom is R minus 1. And the interaction is C minus 1 times R minus 1. So this number has to be, I think you can see that, this number has to be 2. This number times this number gives you this number. Again, the interaction degrees of freedom is defined as C minus 1 times R minus 1. Whatever you have here times whatever you have here gives you that. And once you have all three of these, if you add them up, then you get the between groups degrees of freedom, so that has to be 5. What can we do next? Well, we can add these three up to get the between groups degrees, the between group sum of squares. So 40 plus 60 is 100, plus 480 gives us 580. Next we can go in this direction. There's a couple of different things we can do at this point, but let's do this one. So 580 divided by 5 gives us 116. Nice, easy to work with numbers. I like whole numbers. I don't like writing out decimals very much. I'm sure you don't either. Although we have to sometimes, and when you do, please do take them to the second decimal point for the answers, and the third decimal point if you're doing more computations with it. Now, going down in this direction to fill in the sum of squares to finish this column, 580 plus 244 will give us the total sum of squares, and that comes out to be 824. And so we're sort of stuck over here. We don't know what to do because you need to have two of these in order to get the third, between that one and these two down here. Well, there's a hint on the side. The hint is that n equals 60. When I do this in class, a lot of the time, it takes students a little while to catch that I have that critical piece of information down underneath the table. Well, the total degrees of freedom is defined as n minus 1. So if n is 60, this number has to be 59. And now we can get this, and we can finish the table. That has to be 54. 480 divided by 2, going over here, that's 240. And now we can get the error term because we've got these two. The error term is the number that gets divided up into each one of these in order to get each one of the f-test results. And this number, remember what I said about decimal points, 244 divided by 54 gives us 4.519. We had to take it to the third decimal point. So I'm sad now because we have a lot of decimals to work with, and you know how we feel about decimals. But when you have them, you have to use them. So this number now gets divided into each one of these independently of the others, and that gives us the f-test result for the four different ways in which we're going to slice and dice the data. The between groups is the one-way ANOVA. That just tells us whether there's a difference in there somewhere. And 116 divided by 4.519 gives us 25.669. I don't even have to look up the critical value to know that that is significant. I will look up critical values later, but not on this problem. 240 divided by 4.519 gives us 53.109. 60 divided by 4.519 gives us 13.277. And then 20 divided by 4.519 gives us 4.426. So that completes this set of problems, this set of fill in the blanks. We got one more of these for you. And again, this is one that I did not give. That shouldn't be there. Let me delete that. It's from the previous problem. I copied and pasted and forgot to get rid of that one. So we've got a table that only has 3 pieces of information in it, but we have some text at the top, and it says, assume there are 3 levels of the column independent variable, the column IV, that is not a Roman numeral, 3 levels of the column IV, and 3 levels of the row, should be IV. 3 levels of the row IV, independent variable, and that each cell has 9 subjects. Okay, so what we have here is a 3 by 3 design. 3 by 3 design. You can map it out if you like, or you can just imagine it in your mind. What we're going to end up with is a table with 9 cells, 3 columns and 3 rows crossed with each other yields 9 cells. So if there are 9 cells, 9 subjects in each cell, 9 times 9 is 81. And if the total degrees of freedom is n minus 1, this number has to be 80. So far, so good. We've got a quick result, and we didn't even have to do that much work. Okay, so now for the columns and row degrees of freedom, I like to do the degrees of freedom first, just because they're easy to do. Remember, it's C minus 1 for columns and R minus 1 for rows, where C is the number of columns and R is the number of rows. So if we have 3 columns and we lose 1 degree of freedom of those 3, we're left with 2. And then the same thing here. We have 3 rows, but we lose 1 degree of freedom among the rows, and that leaves us with 2 degrees of freedom for the row independent variable. The interaction then is defined as C minus 1 times R minus 1. In other words, this number times this number. 2 times 2 gives you 4. That goes right here. And, well, what can we do next? If there are 9 cells in this design, if you mapped out the 3 by 3 structure of the design, you'd have 9 cells. The between groups degrees of freedom is defined as k minus 1, where k is the number of cells. So this number would be 9 minus 1, gives you 8, and you can see that these 3 add up to 8, which they have to. Okay, so now we can fill in the top area here. 144 divided by 8 gives you 18. And then moving in reverse, 18 times 2 gives you 36. And what can we do next? What can we do next? It's easy to get stuck on these, and I see students do these on quizzes and tests and get about this far sometimes and get stuck. So you really need to think carefully about what is it that can be done. And here's one. The between groups plus the within gives you the total. So if you have the total, subtract the between groups, and what you're left with is the within. Now the within, by definition, is the number of subjects minus the number of groups. So if we work that way, it would be 81 minus 9. But we can also work this way. 80 minus 8 gives you 72. So, what can we do next? I'm not sure, actually. Let's see. Maybe there's a piece of information that I left out somewhere. Okay, I had to pause the video for a second and think about that, and I did. I left out, I should have had another piece of information in here. It's impossible to solve this the way that it is. So let me give you, or us, one of these pieces of information. Let's say, and I have the answers, so I can do that. Let's say this one is 84. That piece of information should have been in there for us to be able to solve the rest of these. But with any one of these, we can do the rest. So with this one, we can solve the rest. Uh, take 144. Again, this one I just put in there. There was no way that we could have gotten it unless I had the answers, but I do have the answers. So if we take 144, subtract 36, and then also subtract 84, what we're left with after removing those two numbers from 144 is 24, and that goes here, because these three have to add up to this. And now what we can do is 360 minus 140. I guess we could have done that before, but we wouldn't have been able to do the middle part. 360 minus 144 will give us the within. So that is 216. And then going in this direction, 216 divided by 72 gives us the ms within. That's 3. 84 divided by 4 gives us 21. That goes here. And 24 divided by 2 gives us 12. That goes here. Then each one of these numbers gets divided by 3, 6, 6, 4, and 7. And now the table is completed. Okay, moving on to the next problem. And this is the the lengthy computation problem that I asked you to do for homework. We've got this. Let me go to full screen now so that I can use my animations. The very first thing to do is to get the grand mean, and there are a few different ways to do that. I've got the grand mean down here. That's 6. If I take the individual scores here for our two different treatments, by the way, this is a 2x2 factorial ANOVA. Treatment A has 2 levels. Treatment B has 2 levels. This is columns. This is rows. I wanted to get away from calling it psychotherapy and drugs every single time. So in this instance, I called it treatment A and treatment B. So we've got 3 people in treatment in this condition where people get both treatment A and treatment B. 3 people here, 3 people here, and so on. If I take the means of these cells, 10 plus 12 plus 14 divided by 3 is 12, and I can actually compute I can put in the means down. Actually, I guess I do need it in this format so that I can type in. Still a little bit new to making these videos. So one of the things that we can do is we can map out the means like this: 12 and 4 and 3 and 5. So that is just taking these 3 people, adding their scores together, divided by 3. That gives me 12 down here. Take these 3 people, add them together, divide by 3, and that gives me this, and so on. For each one of these, I did the same procedure. Now, if I take 12 plus 4 plus 5 plus 3 and divide that by 4, if I add these 4 cells up, the means of these 4 cells together, that comes out to be 24. And if I divide that by 4, I get the grand mean of 6. But I'll get the same thing if I take all of these numbers and add them up individually. If I add all 12 of these subjects' scores together and divide by 12, I will still get 6. So either way I do it, I get the same answer. Okay, so we have the grand mean, and the thing to do here is to stretch out the scores in a one-way ANOVA, and this is the worksheet that I gave you at the back of the problem. When I first started teaching Factorial ANOVA to students, I used to give them just the numbers and had them calculate it. But what I saw happening again and again is that the computations got really sloppy because this is not something that we're accustomed to doing, and people don't have very meticulous handwriting. I mean, neither do I. And so it's just a lot easier if we use a grid like this that I created using the word table utility. And so I've got my 4 cells. This is, oops, this is the first cell right here. And these are the 3 people in that cell. This is the second cell in the first column. And that's the 3 people there. So if I go back, that would be these 3, right? So what I'm doing is I'm taking all 12 of these scores and I'm laying them out like this in this grid so that I can get the deviation score of every one of these people, telling me how far each score is from the grand mean. And so then I do this one, and that's the top of the right hand side up here. And then this one, that's the last cell. And the means down here, I can put those in. 12, let's see, in my answer sheet. 12 and 4 and 5 and 3. By the way, I will also post a Word document with these answers so that you can just check them. But I thought it would be useful for you to see a walkthrough, an actual walkthrough. Now we've got the grand mean. The grand mean is 6. That's from the previous page. I don't like that. Something else in here. Okay, here we go. So I'm going to take 6. I'm going to take 6 and subtract it from each number. So 10 minus 6 is 4. 12 minus 6 is 6. 14 minus 6 is 8. Negative 4. You see what I'm doing? This is exactly what I would be doing in class. If we had class, I would be drawing this on the board. And that's when I fill up the entire board with numbers. And people start getting a little glossy-eyed. Maybe this is better, I'm not sure. But you can see what I'm doing. I'm taking each score and subtracting 6 from it. 3 minus 6 is negative 3, and so on. This one is negative 1. And notice that these do not add up to 0 like we're accustomed to having our deviation scores add up to 0. And the reason why is because you have to go through all these numbers. If you add up all of these deviation scores, they will sum to 0. But at the bottom of any one of these, they don't do it. We'd have to do all 12 of them. And then just as we did when we, back at the beginning of the semester when we computed standard deviations, numbers that add up to 0 are not useful, so we have to square them. And this is the procedure whenever you do standard deviation or variance. So we square these numbers, 16, 36, 64, and so on, 16, 4, and 0, and 9, 1. Well, you see what happens is we get rid of the negative sign doing this. And then we add them up. And you know, if I added up this set here, that would be 116. If I added up this set here, that would be 20. That's where these numbers come from. If I add up this set, that's 11. And if I add up this set, that's 35. So now we have the solution for the sum of squares total. That's 182. Now we can move on. Now I do have some animations in here, but I guess it's not going to work, and I don't want to start over. So so bear with that. Now we have the sum of squares total. We can put that in here. And how many degrees of freedom between? We've got 4 groups, so that's 3. We've got 12 people, so that's 11. And that has to be 8. It's the number of groups, number of people minus number of groups. 12 minus 4 gives you 8. The next thing to do is to compute the between group sum of squares. So, and here's where I would have had a an animation in my PowerPoint, but well, let me see. Yeah, so let's see what happens here. So if we go back to the the structure of the experiment using the cell means. The cell means are what's important when you're computing the sum of squares between, because the sum of squares between is a measure of how far each cell is from the grand mean. How far is the cell mean itself from the grand mean? So we use the formula for sum of squares between, and it's really the most complicated formula of everything that we do in the semester, I guess. I don't know. There's some ones that are a little more challenging at times. But this, in terms of what we actually do by hand, this is one of the more challenging ones. And the only thing that makes it challenging is that we have these different components we need to remember to use. The actual computations are not difficult at all. What the formula says is it says if we had the original formula, it's n sub j for the jth group times mean sub j minus the grand mean squared. And so what we're doing is we're taking every mean of each cell and subtracting the grand mean from it. So it's this one, 12 minus the grand mean, square that number, and then multiply by the number of people in that group. And when you do that, you know, this is the next stage of computation. It's 12 minus 6 squared is 36. 12 minus 6 is 6, and 6 squared is 36. So that's what we're looking at down here. This represents the computation for the first cell, and then we move on to the second cell. The mean of the second cell is 4, so we put that here. The mean of the third cell is 5. We put that here. The mean of the fourth cell is 3, and we put that here. So now, when we compute all of these, what we get after multiplying what's inside the parenthesis, after taking the subtracting the grand mean from each square, squaring it, and then multiplying that number by its sample size, doing it for each one of these, then adding them together, we get 150. And so that's the sum of squares between. And then what we know about the sum of squares within is that we can use a shortcut. If you have the total degrees of freedom, take the total, which is 182, subtract the between groups sum of squares from it, and what you're left with is the within groups sum of squares. So the total sum of squares, which is this, minus the between group sum of squares, leaves us with the within, because the within and the between add up to the total. Okay, so now we can fill in this much of the table, and that's good. Actually, let me go back. This is where the animation is not working so well, because I wanted to type these in by hand. So the next step is to fill in the degrees of freedom, 3, because we have 4 groups and we lose 1. We already knew these. That was 11 and that was 8. And then the next part is the columns, rows, and interaction. There are 2 columns, so that is 1. There are 2 rows, so that is 1. C minus 1 times R minus 1. In other words, 1 times 1 gives you that. So far, so good. The next step is to compute the sum of squares for columns and rows, where A is the columns and B is the rows. And then we can get the interaction. You can see I also went in and filled in this part. So 150 divided by 3 gives you 50. 32 divided by 8 gives you 4. And then 50 divided by 4 gives you 12.5. Okay, so now we've got, I think I'll just bypass the animations at this point and just stick with what's on the screen. So now we have the individual scores again, and you can see that what I've done is I've put the column mean here for the first column, and the column, that's what the subscript here says. mean sub C1, that's the mean of column 1, and the mean of column 2, that's the mean of these 6 people. If you take all 6 of these people, add them up and divide by 6, that mean is going to be 8. And if you did it with this with the cell means, where this cell mean is 12 and this cell mean is 4, 12 plus 4 is 16 divided by 2 gives you 8. So either way you do it, whether you do it with the raw scores or whether you do it with the cell means and divide by the number of cells, you're going to get the same thing here, as long as you have equal sample sizes, of course. So what we're looking at here is the mean of all these people in the first column, and here we're looking at the mean of all these people in the second column. Over here we're looking at the mean of all these people in the first row, and you can see that these people are going to be counted twice, and that's okay. And then for this one the mean is 3.5. This is our way of telling whether treatment A works ignoring whatever's going on with treatment B. That's the main effect for treatment A, and you see that here in terms of how far apart these are. Just looking at these numbers, we can tell that the F-test result that we get for treatment B is going to be a little bit larger than for treatment A because these means are a little bit further apart. Specifically, what we want to do in order to calculate the sum of squares for the columns and rows is use this formula where we're getting a deviation score that tells us how far is each column mean from the grand mean in squared deviation units. So strictly speaking, we're not really looking at how far 8 is from 4. What we're looking at is how far is 8 from 6, where 6 is the grand mean. And how far is 4 from 6? So again, you can see that these two numbers here are a little bit further apart from each other, and they're going to be a little bit further apart from the center point, which is the grand mean. And you can see that down here that these numbers, this number is a little bit larger. Okay, so back to the computation. If we follow the formula, what we do is we insert the column mean and the grand mean and the mean, rather the n for the number of people in that column. The mean of the first column is 8, the grand mean is 6, and there are 6 people in this column. That's these 6 people right here. And we set that up, and then we move on to the next one. Always remember to do it for all columns, or if you're working on rows, do it for all rows. Over here, the mean of row 2 is 4, rather the mean of column 2, sorry, is 4. That's what we're looking at right here. The grand mean is 6, and the n is 6 for column 2. That's what this 6 represents. And then when you do these calculations, it comes out each one of these is 24. If you have equal sample sizes with 2 columns or 2 rows, these numbers are going to be the same because the means are going to be equidistant from the center point, which is the grand mean. So the sum of squares for the columns is 48, and that's going to go directly into our summary table. And then I do the same type of computation down here. I will not walk through this one, but you can see the computation. That comes out to be 75. And then the interaction is what's left over from the between groups after you remove the other 2. So the between groups sum of squares was 150. We're going to subtract the combination of 48 and 75. 48 plus 75 is 123. 150 minus that leaves us with 27. Okay, so now let's go on to the next page. Treatment A goes here. That was 48. Treatment B sum of squares was 75. And the AB interaction is what's left over after you take these two numbers out of 150, and that is 27. Now moving this way, well, we can just copy and paste these. How about that? And the reason why is because the degrees of freedom for each one of these is 1. 48 divided by 1 is 48. 75 divided by 1 is 75. 27 divided by 1 is 27. Now we're going to take each one of these and divide it by 4, and that gives us the answers that we want. And we're almost done. Just a couple more minutes of the video left. I will not be graphing it out this time. I'll save that to my next video. So there are the answers. And we also are interested in the critical values for F. I don't know what's... Oh, I see. Need to... well, I'll worry about that later. When I look up the critical values, I don't have the figure from the back of the book handy, but I think everybody knows how to use that at this point. The critical value, when you have 3 degrees of freedom in the numerator, 8 in the denominator, the critical value at the 0.05 level is 4.04. We got a little bit of a formatting problem here. The numbers are popping up at the top of the box. And all of these are the same. So what we would conclude, comparing each of these F-test results against each of their critical values, is that every one of these F-test results is greater than its comparable critical value. In other words, each one of these F-test results is significant. Now, how do we, what do we do with that information? The Way Anova is up here. The fact that that one is significant simply tells us there's a difference in there somewhere, but it doesn't tell us where. What you'd really want to do is go and look at the Bonferroni post hoc pairwise comparisons, or some other pairwise comparison system like the LSD test or the Chiffet, etc. So that's what that one tells us. The column result here for the treatment A, which is the columns, we call that the main effect of columns, or the main effect of treatment A. And the fact that that one is significant tells us that yes, treatment A had an effect. If we go back and look at it, we can see that effect right here. The people who got treatment A scored higher than people who did not. That's the main effect of treatment A. And then going back to the summary table, we look at treatment B. Treatment B is a little bit stronger. That's the main effect for treatment B. And that is telling us that when we look at the rows, this number compared to this number, the people who got treatment B scored significantly higher than the people who did not get treatment B. That is the main effect for rows. In other words, we're able to test both of these independent variables simultaneously. And going back to the summary table, we've got one more, and that's the interaction of A and B. Well, how do we think about that? How do we think about the interaction effect? In order to do this, we need to look at the structure of the 2x2 table with the cell means in them. So I'll go back to this page where I have the cell means, and what we see is that people who got both of these things really scored a lot higher. So that is an interaction effect when you have both A and B being given to our clients or patients. You can see that they respond particularly strongly compared to if they only got treatment A or if they only got treatment B. This cell over here, they only got treatment B, and this cell over here, they only got treatment A. So that is an example of a significant interaction effect. Okay, well, that's all that I wanted to cover on this one. If I were taking it another step, I would do the figure that shows you the 2 different lines for the independent variables, but I'll save that for the next video. And stay tuned for more. I'll be uploading more. Perhaps I'll be able to record the next one in the coming day or two. Thank you. Bye.